Let's look at a slightly more complex situation. Let us look at a situation where, again, we have a system which, again, we divide into two halves. But the difference to the previous case is that the system is not isolated anymore, but it's coupled to a heat bath. Later in the course, we'll talk in more detail about heat baths. The basic idea, heat bath is sometimes also called a thermostat, is a system that is very large, it's at a fixed temperature, and it's in thermal contact with your system of interest. And it has the effect that it keeps the temperature of your system constant. So the heat bath keeps the temperature of your system fixed. Now, when we look at the distribution of energy, particle number, and volume, in this first case, we still have U half, N half, V half on the left and likewise on the right. But in our energy balance, we have to account for the energy of the heat bath as well, because your system of interest and the heat bath are allowed to exchange energy in the form of heat. Yeah? So you have to take into account the energy of the reservoir. Now this, on the left-hand side, you have the homogeneous state. On the right-hand side, as before, you have the inhomogeneous state. And in this case, let me make the division in such a way that you have on the right-hand side, sort of in this inhomogeneous scenario, you have on the left-hand side, you have a smaller volume than on the right-hand side. So you have on the left, you have half the volume minus some delta V, and on the right-hand side, you have half the volume plus some delta V. The particles are distributed evenly, so you have on both sides you have half the total particle number. And as for the energy, it's a bit more free. I just write U left and U right, and I leave it open how the energy is distributed between left and right. And we still have to consider the heat bath T that keeps both halves of the system at a fixed temperature T. And it is possible that in the course of this separation, that the system has exchanged energy with the heat bath. So we allow for the possibility that the heat bath now has an energy U of the reservoir, as on the left-hand side, plus some delta U. Now we still require that the system settle in the homogeneous phase. So we require that the homogeneous state is stable also in the presence of a heat bath. So again, we must require that the entropy associated with the left scenario, where the system is in a homogeneous state, is strictly larger than the entropy of the scenario on the right, where it's inhomogeneous. But we have to be careful that we include the reservoir. So we have to look at the total entropy of the system of interest plus the reservoir. Because the two systems are coupled, and it's the combined system, including the reservoir, that settles in a certain state. And we want to make sure that it's the one where the system of interest is homogeneous. Now, mathematically, we proceed with a similar logic now. We say in the left scenario, the total system of interest plus reservoir is the entropy of the left half of the system, which is this function S system at half the total energy, half the particle number, and half the volume. We have that for both the left and the right, so we have a factor of 2. And we have to add the entropy of the reservoir. That's the total entropy on the left, in the left scenario, in the homogeneous scenario. And this must be strictly larger than the entropy of the inhomogeneous scenario. What's the entropy of the inhomogeneous scenario? It's the entropy of the left half of the system, which is this function S system evaluated at energy U left, half the particle number, and volume V half minus delta V, plus the entropy of the right half, that is this function evaluated at U right, half the particle number, and volume V half plus delta V. And then we have to add to that the entropy of the reservoir. The entropy of the reservoir may have changed with respect to the homogeneous scenario, because the energy of the reservoir may have changed. Remember the differential of entropy, ds is equal to k beta du. So when the energy of the reservoir changes by delta U, then its entropy changes by k beta times delta U. So the entropy in the inhomogeneous scenario is now its original entropy plus k beta times delta U. You see that the entropy, the original entropy of the reservoir, cancels out in this inequality, and we are left with the remaining terms. Now we can evaluate the system, the entropy of the system, using its relationship with the log of the partition function. And here I would like to work in the canonical case. So here I would like to consider the canonical case, because then I can write the entropy of the system. I still have a factor of 2 here. Its entropy of the system is k times log of the canonical partition function. The canonical partition function has as its natural variables beta, the Lagrange parameter beta, the particle number, and the volume. So the entropy is this log of the canonical partition function plus beta times the energy. We still have the factor 2 in front, and we have k, beta, and the energy is U half. this must be strictly larger than the system entropy of the left half in the inhomogeneous scenario, which again I evaluate with the canonical partition function. That's k log canonical partition function evaluated at beta half the particle number and volume v half minus delta v plus k beta u left. And then I have the entropy of the right half, same logic, k log canonical partition function at inverse temperature beta, n half, v half plus delta v, and then I have plus k beta u right. And then I still have the contribution from the reservoir. I still have the k beta delta u. Now I used in all the expressions, I used the same beta, which I'm allowed to do because the system is coupled to the thermostat. The thermostat keeps the temperature fixed everywhere. So both in the homogeneous and in the inhomogeneous scenarios, on the left and on the right hand side, we always have the same temperature. So the beta is the same everywhere. Yeah? So this beta, that beta, and so on, all the betas are fixed by the thermostat. You must have energy conservation. So this implies that these terms all cancel, because u left plus u right plus u reservoir plus delta u, that's what you have on the right hand side, must be equal to u plus u reservoir, and therefore these terms that are just cancelled out, these terms cancel. And let me just write the last line. As a consequence of that, you have an inequality. You can divide by a factor 2k, and then you get an inequality that the log of the canonical partition function, evaluated at beta, half the particle number and half the volume, must be strictly larger than 1/2 log canonical partition function at beta n half v half minus delta v plus log of the canonical partition function at beta n half v half plus delta v. You see you have a structure that is very similar to the condition that we had previously for the entropy. Now we have this condition for the log of the canonical partition function. Again, it will lead to concavity, but this time concavity of the log of the canonical partition function. On the previous page, we had derived this inequality that involves the log of the canonical partition function. And very similar to the case of the entropy that we had studied in the scenario before, we can sketch a figure where on the vertical axis we have the log of the canonical partition function at some given beta, at half the particle number, at some variable volume v primed, and v primed is the independent variable that we have on the horizontal axis. beta and n are fixed, and the above inequality tells us that, as in the earlier case that had involved the entropy as a function of energy, that this log of the canonical partition function must be concave. So again, if here we have half the original volume, and then we vary that by plus or minus some delta volume, and we get values, different values then for the log of the canonical partition function, the inequality tells us that if we connect these outer values by a straight line, we interpolate linearly, then the interpolation of these two values must be strictly smaller than the log of the partition function at the central value v half, and this is nothing but a condition for concavity. So we find that as a function of volume, the log of the canonical partition function must be concave. And again, this can be written in differential form as a condition for the second order derivative with respect to the volume of the log of the canonical partition function. This must be strictly smaller than 0. What is the physical meaning of this condition? We had seen in the case of entropy as a function of energy, the physical meaning of the concavity condition was that the specific heat has to be non-negative and finite. Let's see what the physical meaning of this concavity condition is. Remember the meaning of the first order partial derivative of the log of the canonical partition function with respect to volume at fixed inverse temperature and particle number. You remember from our table and our general scheme that this first order partial is beta times the pressure, inverse temperature times pressure. So the second order partial derivative with respect to volume at fixed inverse temperature and particle number is then beta. Since beta is fixed, this is just a constant prefactor times the partial derivative of pressure with respect to volume at fixed inverse temperature and particle number, and this must be strictly smaller than 0. And this in turn implies, or this is equivalent with requiring that we can take the inverse of that, the partial of volume with respect to pressure at fixed inverse temperature, but inverse temperature, keeping inverse temperature fixed is equivalent to keeping ordinary temperature fixed at fixed T and particle number, that this is also less, and in this case possibly equal to 0, because the partial of pressure with respect to volume, it must be strictly smaller than 0, but it can in principle approach minus infinity. When we take the inverse of that, then the inverse is again smaller, but it can also be equal to 0 in case the original partial derivative approached minus infinity. So here we have the condition that this is less or equal to 0. If we introduce a minus sign here, then this must be larger or equal to 0. And finally, we can, it doesn't hurt to introduce an extra factor 1 over volume in front. volume is always positive, so this doesn't change the condition. But then the left-hand side is just by definition the so-called isothermal compressibility. It tells you how at fixed temperature, fixed particle number, how the volume changes in reaction to a change in pressure. And this is why it's called the isothermal. Isothermal meaning at constant temperature, and compressibility meaning how the volume changes, how it can be compressed, or how it is compressed when you increase the pressure. So we find as a physical meaning here that the isothermal compressibility must be non-negative and finite. So here, in fact, we also have on the left-hand side another inequality, that this must be strictly smaller than infinity, that this must be finite. While the derivation of these conditions, starting from the homogeneity and stability conditions for a fluid, is more recent, the requirement that for stable matter you must have a non-negative specific heat and a non-negative finite isothermal compressibility. This had been known for a much longer time already, and it was known as Le Chatelier's principle. For a substance to be stable, you need it for both the specific heat and the isothermal compressibility, that these are non-negative and finite. So expressed in words, this means that a system, and here we've been talking about homogeneous fluids, is stable if, well, the fact that the specific heat is non-negative says physically that heating increases temperature. And the fact that the isothermal compressibility is non-negative says physically that isothermal compression increases the pressure, or in other words, increasing the pressure leads to compression, i.e. a reduction of volume. Yeah? So isothermal compression increases its pressure. And as a result of that is you have that whenever you create a heterogeneity, so for example you have the system, and then by force you have a gas in a container, and then by force you push some of the gas in one corner of your container, then this will increase the pressure in that corner of the container. And this increase of pressure ensures that when you leave the system alone, it will settle in an equilibrium where the gas returns to the other side of your container, so the system restores its previous homogeneity. Likewise, when you heat the system at one end and you cool it at the other end, and then you stop doing that and you leave the system alone, it will restore its homogeneous state, because heat will flow from the hotter to the colder side, and it will restore homogeneity. And this is This is ensured by these two conditions. So to complete my sentence, whenever one creates a heterogeneity, then the system will respond, once you leave it alone, it will respond by restoring homogeneity. Yeah, so take as an example what I just told you in words. You have a system here that is homogeneous, and then you have you introduce a piston here, and you push it. You push the system. You push the piston to the right, so you decrease the pressure on the left-hand side due to the non-negative isothermal compressibility. When you do that, you push the piston to the right, this will lead to an increase of pressure on the right and a decrease of pressure on the left. So when you let the piston go, then this pressure difference will push the piston back, and the system will restore its prior homogeneous state.